Greetings and welcome once again to the new Calculus channel, and my name is John Gabriel, and I'm going to try and explain to you once again the historic geometric theorem and pretend that you're just a freshman in high school. So what you're looking at in front of you is a post by some idiot called Fritz Feldhasser on sci.math. Now he's a specifically bad person because he lies, for one thing, continuously, and he misrepresents the facts. So I'm going to show you now in this video what exactly the historic theorem is about, and I'm going to show it to you using only geometry. So, of course, for the complete proof, you'll need to look at the article on the historic geometric theorem. So let's begin, right? So what does the theorem tell you? Well, when I revealed the historic geometric theorem to the world, I made it clear that h, this h here that you see here, cannot be zero, and that it's a constant, okay? There is no non-parallel secant line, this red line, yeah, that has more than one h, because this would imply that the difference, q of xh, can be more than one slope difference for a given secant line. The notion is absurd. If you have that secant line, it has only one slope, okay? And the slope is 1.37. And if you have that one, it has only one slope. You can't vary q of xh as the morons of mainstream believe you can, right? So neither x nor h, neither x here and h here are variables. That's completely wrong in the theorem. Neither of them are variables in the theorem. Both are constants, and one cannot simply replace or discard either without violating the truth of the identity. The truth of the identity is that the secant line slope, which is this expression here, is equal to the tangent line slope plus the difference. So the reason h is allowed after simplification is due to the fact that it is equivalent to discarding or ignoring the slope difference. It's equivalent to discarding this 0.5, which is 2 divided by 4, right? 2 divided by 4. The derivative is 4 divided by 4, which is 1, and the difference is 2 divided by 4, which is a half. So look, when you write the equation of a straight line, like y is equal to mx plus c, so I don't know if I've got a freehand shape. So if you write y is equal to, that's not working properly, so I'm not going to do it. I don't know why that's happening. But if you write y is equal to mx plus c, you can ignore the y-intercept c if all you want is the slope m, right? You're not saying that y is equal to mx by ignoring c. So the same thing happens here. You're not saying that q of xh, which is the slope difference, by ignoring it, you're not saying that this is equal to the derivative, because the only time that this expression is equal to the derivative is if this red line is the tangent line. That's the only time. So if all we want is the tangent line slope, then we can ignore the difference, right? Which is equivalent to setting h equal to 0, or even taking the limit as in the flawed mainstream calculus, okay? So, and I'll explain a little bit later on why it's flawed. So there are three possible cases with the identity, with this particular identity. So the first case is that the secant line slope lies above the tangent line. The red line lies above this line, and therefore the difference must be positive, right? There's the other difference, the second case, where the secant line lies beneath, okay? So if we extended this tangent line, it would be up here. So in a sense, it lies beneath, and it means that the slope difference must be negative, right? I'm not considering the negative side here. I'm only considering the positive. But you can download this applet if you want, and you've got good eyesight. You can do the same thing on the side here. I'm not going to do it, right? Now, then there's a third case where the secant line is the tangent line, meaning this. In other words, there's nothing there but rise over run. Now you cannot say that this slope here, which is a derivative, is the same rise over run as the secant line. They're not the same, because the secant line will be this plus this over this, right? 2.32 plus 4.31 over 4.31 will be the slope of the secant line, which is 1.54. But we know that the slope of the tangent line is just 4.31 over 4.31, which is 1. Now, the rise over run in the third case is not the same as the rise over run of the tangent line unless f is linear. And as we can see, f, the blue line here, it's not linear, okay? So this is what I discovered. And I had to in some way relate the non-parallel secant line slope, this slope here, to that of the tangent line. And so I said, okay, what I need to do is I know the non-parallel secant line slope, and I can call the tangent line slope by f prime of x, right? So there's nothing magical about f prime of x. I could have replaced this expression here by tangent line slope, because the tangent line slope is equal to the rise over the run, okay, of the tangent line. So the non-parallel secant line slope will be equal to the slope of the tangent line plus the slope difference, okay? So there is never any finite difference. So there's never any finite difference here, like this expression here, which that can represent the tangent line slope. So you see how flawed mainstream is? It doesn't. F is not the same line as the tangent line unless f is linear. So the obvious answer is that these slopes have a difference that is comprised of an expression q of xh, which is this expression here, which is by no means an error term. Did you get that? It's not an error term, ever. But that value which keeps this identity true. In other words, q of xh is a fixed value which keeps this non-secant line slope equal to the sum of the tangent line slope plus the difference. It cannot be an error term, like the effing morons on sci.math call it, okay? And they never knew about it until I told them. Then they decided it was an error term. Bunch of monkeys, you know. Now suddenly all of them are admitting that you can do it, whereas in the past they were all libeling and lying about me and calling this identity a bunch of crap. So even the monkey business of taking the limit of q of xh, or the limit of this, is not allowed because the identity is not true. The identity is not true since the non-parallel secant line slope is never equal to a tangent line slope unless they are the same line. Okay, so this is all very simple knowledge, but no one before me was able to realize it. The reason is that I'm a genius and the majority of you are incorrigible morons. Yes, it really was that simple, but no one before me was able to see it. So what I've given you here is the Holy Grail of calculus, because from this one identity, you get the derivative and you also get the definite integral, which is just f prime of x plus the slope difference times h, gives you the area under the curve between 4 and x plus h, which is this distance here. Okay? So that's pretty much it. Wow, that was extremely tiring. I'll leave you with that, and who knows, maybe there will be another video, maybe there won't. Till next time, goodbye.